models networks, right? So I'm interested in finding these groups, right? Dividing networks that we find in the real world with, groups, putting colors on nodes, right? And I want to do this from a point of view of generative models and inference. So I want to define models, right? We generate networks using probability and has as part of its parameters the partition of the nodes into groups. And then I want to compute the Bayesian posterior of this, so the likelihood of having a partition given the data, right? And I want to essentially find partitions according to this probability, right? The inference, which involves computing, specifying the prior probabilities for these things, and let's say integrating over the other parameters that we're not particularly interested in, even prior probabilities on them as well. Now, this is done. The simplest model that incorporates these properties is the stochastic block model. Right? People have talked about this quite a lot here. There are a couple of different variations of the stochastic block model. Here are the two most basic ones. One is the Bernoulli type. Perhaps it's most used one, where you say that this is the existence of an edge is given a probability that is conditioned on the group membership of the nodes which it connects, right? So this set of parameters that we have in addition to the partitions are these edge probabilities. Another version is the Poisson stochastic block model, where we say, okay, instead of a Bernoulli, you have a Poisson variant here. The nodes are sampled from a Poisson with a given average, which is also conditioned on the group memberships. Now, this would generate a multigraph, naturally, because it's a Poisson. Now, you can say that it doesn't really matter in the end, because if the graph is sparse, then most edges are going to be either 1. Most values are going to be either 1 or 0. The probability of having 2 will be very small. And one usually chooses between these two things depending on whether or not some computation is easier or not. What I'll do here is actually use a third variant, which is less often used, which is what I call the microcanonical stochastic block. So I'm borrowing here terminology from physics. So microcanonical means that I have hard constraints. So instead of saying I have a probabilities or average number of edges, I have really the total number of edges, right? So I have a matrix here giving the exact total number of edges between groups R and S, right? It's an integer. So why we'll do this? For two reasons that will become clear throughout the talk. One is efficiency. Actually, doing it in this way gives us a model that is very efficient to infer. In particular, not only will we be able to tackle large networks, but we're going to have a likelihood of inference procedure that will be algorithmically independent on the number of groups that we are using. Right? This is not typical, especially in the Bayesian. Usually things become more expensive as you increase the number of groups. In this case, this will not happen. And perhaps, let's say equally important is that I'll be able to use deeper Bayesian hierarchies. I'll be able to replace, let's say, non-informative priors on my parameters by a sequence of priors and hyperpriors, which will solve some important problems. Right? They are there because it will make things better. And the reason why this is second thing it happens is indeed because it's inherent in this formulation that some calculations are simpler. So in the canonical way of doing things, right, if these parameters are real values, in order to compute the posterior, you have to compute this marginal likelihood where you integrate over the parameters. Now, if you have a Meyer canonical model, the parameters are discrete now, so you have to sum over them. But because of the hard constraints, there's actually only one term of this sum which is non-zero. This is pretty much the definition of what the microcanonical model is. So there's really no difference between the joint likelihood and the marginal likelihood. There's only one parameter that actually makes sense given the data. This propagates also to when I replace here the prior by a condition prior on a hyperparameter with its hyperprior. And the sum also will be trivial. There's essentially I have to consider here the joint. So which means that the only job I have with this sort of model is to write down the likelihood. And then it is simplified. So if I can write down the likelihood, the joint likelihood here, I'm done. Okay. Another thing is that if you look here at the posterior, right, which is involves this marginal, which is the same here as the joint, the log of this thing has an interpretation which is the description length of the data, right? I can write it as in two terms. One is the likelihood of the data given the model parameters, and the likelihood of the model parameters. This is the amount of bits. Let's see if we use base 2 here. This would be the amount of bits I would need to describe the data, and this would be the amount of bits I need to describe the parameters. And this whole thing gives me indeed how many bits I need to specify everything. And it also explains why this includes already regularization. Right? Essentially, if I increase the size of the model by, let's say, increasing the number of groups, this thing here will decrease, but this will increase. And then if I minimize the whole thing, I'll find the sweet spot between these two things, right? I will find the maximum compression of the data, and this will give me a way of indeed selecting, for example, the number of groups. This connection between this minimal description length approach and Bayesian approach is much more general, but here it's pretty straightforward. Essentially, they're essentially equal, right? I'll use this analogy, this interpretation here throughout the talk as well. Good. So before I go further into how I specify my model, how I work with it, I'll talk about degree correction. So the traditional stochastic block model is something actually in practice works not so well. This is an example here by work by Brian Carter and Mark Newman. This is the political blocks network. If I use two groups, if it is the stochastic block model, it gives me this very unsatisfying fit where instead of finding here these groups, which are Republicans and Democrats, it splits me into high degree and low degree, because that's what I expected with the stochastic block model, that nodes that belong to the same group have on average the same degrees. Therefore, it actually prefers, in this case, to cluster according to the degrees. And the way that Carr and Newman solved this was by including more parameters. They say, okay, let's put here some node propensities, some probabilities of receiving edges on all nodes, and this will give us the average degree of the node, regardless of to which group it belongs. This indeed corrects for the degrees, and if you fit this for this network, it gives what we wanted to find, let's say. But the way that it is done, it's pretty convincing, but it solves this problem by adding more parameters. So something we're able to tackle here is, to what extent these are really necessary or not, right? Becomes a problem of model selection. I will work indeed with a degree corrected model at first, and then we'll get a non-degree corrected afterwards as a special case, and able to compare these things. So how do I make my microcanonical degree corrected stochastic block model? First, I start with a partition. I put nodes into box. Then I specify the edge counts between groups, right? Please note this probability. I say there must be this many edges between groups. And then, conditional these two things, I sample the degrees somehow. I specify the degrees by the spokes here. And then I pair these half edges, respecting these constraints, right? So it's a generalization of the configuration model. So this will generate me, in general, parallel edges here and self-loops, but I use the same argument as the Poisson model and say the probability of this happening will become very low if the graphs become very large and sufficiently sparse. Right, so this is a model. It's pretty simple. It's physically the same thing that's really happening with the stochastic block model, but there are certain types of fluctuations that I'm forbidding, right? So always the same number here and so on. Good. Let's go through these things one by one and seeing how we put priors on them, what's the effect that it has. So first, the model itself. So I have here these parameters, and I want to compute the likelihood of observing a given graph. This is fairly easy. I just have to compute here the number of configurations that this constraint allows, which is given by this. But I am interested in graphs. There are many configurations that generate the same graph, but I can count them, which is this. It's a very similar expression. So I make the ratio here. I have the likelihood of observing a graph or a multigraph. That has a pleasing expression. Anyway, this is easy part, the model. Let's think about the priors, right? I have to say here what's the probability of observing a partition, the prior probability of observing a partition. The simplest thing we can do is assume a non-informative prior, essentially a flat prior. I simply count how many partitions there are with a given number of groups. Right? This is a bit ugly here because in my model it's actually easier for me to say that to forbid non-empty groups. So groups must be occupied. Okay, this is the simplest thing we can do. It's not, however, the best thing because it assumes implicitly that all groups have the same size. Something better we can do is go up a little bit in the Bayesian hierarchy and condition the partition on the sizes of the groups, and then we sample the sizes from a flat distribution, from a non-informative distribution, right, with a given number of groups. And we can write the likelihood very easily. And one reason to see why this is useful to do this kind of thing is that if you take the log of this, and you assume that you have sufficiently many nodes, this is decomposed into two terms. One is the entropy of the partition plus a logarithmic term, has to do with this hyperprice. And this grows linearly, this goes logarithmically. With sufficiently you can ignore this essentially by wash out, and I have the optimal encoding. This is the description length of this. So if I were to replace this with another set of priors, I would get at most a correction here, which is logarithmic, so you get this diminishing return if you keep going up in the Bayesian hierarchy, right? So this seems like a good place to stop. Let's keep going. It gets a bit more interesting. The degrees now. How do you set the prior for the degrees? I'll call here, perhaps the simplest thing you could do is I'll call it this option 0, which is that you take here these half edges and you drop them randomly on the nodes. This is write out a likelihood. If we do that, the distribution of degrees that you expect will be a Poisson, and this is essentially the non-degree correct stochastic block model, which happens here as a special case of the degree correct stochastic block model. Right, this is, as I showed, not a good idea because it will assume implicitly always that the distributions are Poisson. So let's assume then that all degree sequences are equally likely. So we sample them here in each group, right? We count how many degree sequences there can be, and 1 over this is the probability of each one happening. If we do that, however, the expected degree distribution, the frequency, is exponential, right? This is the maximum entropy distribution with a constrained average. So it's not too much of a difference. In the way we instead of expecting a Poisson, we expect now an exponential if we do this. So let's go a little bit further. Let's condition the degree sequence on the frequencies of degrees, like we did for partition, and then we sample the frequencies from a flat prior. So say all frequencies are now equally likely. Now, if we do this, we get this distribution on average, right? So this is the Poisson we had, this exponential. Now we get this thing, which is much broader. So typically, if you sample randomly from frequencies, from distributions, you have a much flatter thing. In fact, there's an analogy here. So again, I just have to count how many distributions there are with a given number, maximum number of nodes, and a given number, sum of the degrees, right? The average. This thing is in fact equivalent to the microcanonical partition function of a boson of a Bose gas, a Bose-Einstein, which follows the Bose-Einstein statistics, right? So you can view this as the nodes as being bosonic particles, and the energy levels are the degrees. The nodes are indistinguishable. So we know here from statistical physics that this actually I'd be very to show that the expected frequency or the occupation levels follow this function, right? The Bose-Einstein distribution. And we can show easily also that things become very large, then the body here, the bulk of the distribution will approach, in fact, a polar law with exponent 1, right? And then there will be an exponential cutoff. Right, so you must say, this is okay, fine, you made your nice analogy with physics, but who cares? I mean, okay, I have this distribution, that, and that. Distribution I find in the real world are something else, so that's the point. No, there is a point here, in fact, the same one as before. If you look at the log of likelihood here, if things become sufficiently large, sufficiently many nodes, then you have two terms again. One is the entropy, and you have a term that grows with the square root of n. So which means that if things become sufficiently large, if there are sufficiently many nodes, at some point I will have here the optimum description length, right, of this degree distribution, regardless of what shape it has, really. And if I would somehow go up here in the Bayesian hierarchy, I would at most have a correction of order square root of n, right, which is not that big. So we are actually here able to learn let's say the 2-degree distribution, at least in an asymptotic limit. Good. there is a snag here, which I haven't talked about, which is how to compute these Qs here, these quantities. This is equivalent to a known problem in combinatorics and number theory, which is the number of partitions of integers, or restricted partitions here. So what the count is, how many ways I can split an integer in other integers, so that there are the sum, right? To m, there are most n parts. In fact, you can compute this exactly, but via a recurrence, right? So with this, we can indeed compute a full table here for these two parameters in a quadratic time, right? At most, with the parameters ranging from 0 to m, we can compute this in quadratic time. So what I could do is just compute a big table before I do the inference, and then I go on. But still, I want to claim here this is efficient, so having quadratic dependencies on arguments is such a good idea. They are, thankfully, good approximations of this. In the 50s, people cared about this a lot, so they computed. There are some very good approximations. It looks a bit complicated, but it doesn't affect the performance of the algorithm. And the approximation is quite good. So here we have, I'm showing here the exact value compared with this, and the values you get with this, and they're pretty much on top of each other, and you can show also that the absolute value goes to 0. So essentially what I'll do is that I'll compute here these things for sufficiently large m, like 10,000 takes about a second, and then you replace with this for even larger arguments. So we can actually tackle things which are very large. Good, let's keep going. The remaining piece now are the edge counts, right, between groups. How do I specify, specify prior here? Again, the simplest thing you can do is be non-informative, but simply count how many possibilities there are, and probably is 1 over that, right? Now, here comes a problem again. So I'm not doing this just for fancy things. I mean, these things, they have problems with them, but I have putting this flat prior. So let's play here a little game. I'll consider a planted partition. So it's a very simple, specific case of the stochastic block model. So I just have big groups, which have uniform size, and all of them have the same number of edges inside of them. There are no edges across them. Right, you can write here, if things, let's assume, for simplicity, that the number of nodes is very large. It's a sparse network, and the number of groups is also very large. If you do that, you write for the whole likelihood that we have so far. You just keep the leading terms, and you can look at how it looks like, has a simple form. Now let's play this following game. This is what we know. We know the groups, know the true likelihood of the model have generated. Let's now consider an alternative partition where I group, let's say, these two communities here, two groups 1 by 1. So the topology network is the same. I'm just saying that now they have the same color. Now this is also a planted partition model. I'm just having rescaled the number of groups, which means I will just have halved these, the value b here. So I can ask the question, what is the best number of groups that these things find, right? And you do just optimizing this function here, and you get that the maximum number of groups that you can find here scales with the square root of n, which is easy to understand. The cost here that occurs from my flat prior for the measure of edge count scales with the square, right, of the number of groups. So I have the square number of groups. This is the number of degrees of freedom I have in my matrix, essentially. And as soon as this becomes the square root of n, this competes with these other terms. And I will start clustering things together, which I know don't belong together, because I put them there. This is not a very nice position to be in, because we know these groups are not there. We know they're quite different. But nevertheless, this thing imposes a limit on the number of groups we can find. Now, this is a bit annoying. So how do we fix this? The same way I have to fix it so far. Let's try to get rid of that, right? And we still don't want to be biased. Of course, if I knew how many groups there were, I knew there was a diagonal matrix, then of course it would be simpler. But let's keep things in general. We can have them. So let's condition things. So this is what happens here. This is a network we have. The groups are the colors, and this is the matrix that we fit. Again, this is like a multi-graph. So what kind of model can we use for that? Well, we use again the stochastic block model, right? So we put another stochastic block model on top of this one. We partition the groups into groups and fit another stochastic block model, and we have the same problem again. Just keep going. At some point, there's going to be only one group, and then we stop, right? So we have a sequence of stochastic block models one on top of each other, a sequence of priors and hyperpriors, right? And it's easy to write the likelihood for these other levels. It's just again the, now I'm not using degree correction for reasons that I don't want to go into. The likelihood is fairly easy to do it. And then if we can play the same game again, let's apply this now for the partition model. I will skip the gritty details here, but the point is that this term, which is scales with the square of the number of groups, becomes now log linear with this. And therefore, the maximum number of groups I can find scales with n divided by log of n, which is much, much better. So I can find now really a large number of groups, or in other words, I can find small groups in very large systems. And this is not just some fancy thing. You can actually verify this with real data. So here, each point here's a real network, right? And the range here, look, the number of edges is across many orders of magnitude. And here's the average group size that I find by inferring this flat model, essentially with a flat, with a one level in the hierarchy. And as a guide to the eye, I'm putting here a square root of v slope. And indeed, as the networks become large, the number of groups also becomes large. Now, if I use the hierarchical prior, essentially I have a cloud. This region is impossible to have. I cannot have more groups and have edges, but all in the entire range where things are possible, essentially I find everything depends on the structure of the net. Right? So I get rid indeed of this problem. Okay, now let's go back to put everything together. I have a model that looks like this. I have the likelihood for the data, for the degrees, and then here for these hierarchical levels. Just to put all the cross the T's and so on, I could say, okay, this actually is still conditional on the number of groups itself, on the number of edges itself, and the number of L, the depth of the hierarchy. It's not really important. I can put any prior I want on these things. It will not affect. They're just simple numbers. They will just be lingering constants in the likelihood. You can put whatever you want. It doesn't matter. Good. How to infer these things? This is important. I will be using here Monte Carlo, right? I'll be moving nodes from one group to another group, though accepting them according to the correct likelihood, the ratio. And the important point here is because of the way that even all these terms that I've talked about, all these priors, it's easy to see by looking at the likelihood that if I move a node from a group, it requires a number of operations proportional to the degree of this node. It doesn't matter how many groups there are in total. And this is a feature that only happens, as far as I know, for this model. Right? So it doesn't, if I'm moving nodes around, it doesn't matter how many groups I have in total. And this is if I do a whole sweep of all nodes in the network, this can then times OE, right, the number proportional to the number of edges, independent of how many groups I have. Now, if you compare, for example, here, there are two examples which it's a bit comparing apples and oranges because they are semi-parametric, they're not full Bayesian, but nevertheless they are presented as very efficient methods. If you do expression maximization with visual propagation, the whole thing scales with the square of the number of groups. There's a variation of Bayes approach that scales linearly with the number of groups, so it'll be better. Now, more connected to what I'm doing here, you can do a Bayesian version of the Bernoulli stochastic block model with uninformative priors, and the greedy approach used here is, again, square the number of groups. So Mark here has an approach also with a +1 model, which also squares the number of groups if you use Gibbs sampling. If you use metropolization, you can get this down to linear on B, but still it's going to be dependent on the number of groups. Right? So this will limit a lot, you know, the performance you can have on large networks. Now there are other things we have to take care. It's not sufficient just to have a model where you can move things around efficiently. You still have an algorithm that exploits this well. So for example, if I were to move, if I have 100,000 groups at my disposal, and I'm moving things randomly, this will be a waste of time. Most of the attempts will be rejected. So I have to be smarter about this. So we do this here by looking at the neighborhood of a node. So suppose you're going to move this node around. I look at a neighbor, it belongs to group T. Then look at the block matrix. And I see T is connected to these groups with given weights. And I sample these from these guys according to the probability. So I inspect the known group information up at this point to better inform my guess. And this works very well, and you have very fast mixing times, and it scales well also with very large number of groups. In addition to this, it's not sufficient. It's a bad idea. There's a problem of initialization of this whole thing. If we just start from a random partition of the nodes into groups, you're going to get trapped in local minima. It's going to take a long time to calibrate. So I use this agglomerative initialization. So I think it's very simple. You just put, for instance, each node in their own group at the beginning, and then you merge groups together using the same rule. And you keep doing that, and because you're moving many nodes at once, this has the capacity of skipping metastable states, right? So we have something that really does scale well.
Tiago?
Yeah.
Both of those tricks seem to assume the network is assortative.
No, absolutely not. That's an important point. So I don't copy what my neighbor says. So this is, right, it belongs to group R. I look, it belongs to group T. Then I look at their neighbors here. So it's explicitly designed to avoid it. So for example, let's say I'm Brazilian.
I changed my color to one of my next nearest neighbors, 2 steps.
On the block graph, not my neighbors on the network. So for example, I'm Brazilian, you're American. Americans are connected to Canadians, so maybe Canadian. Right? So it works well. Okay. Good.